Okay, great. So our last speaker of the session is Chris Granade, who's going to tell us about Bayesian acronym tuning.
All right, well, thank you very much. As mentioned, I'll be talking today about Bayesian acronym tuning. This is joint work conducted at the Quantum Architectures and Computation Group over at Microsoft with John Gamble and Nathan Wiebe. So by way of context, what problem are we trying to solve? Well, we're trying to build a quantum computer. And one of the things that we have to do in order to build a quantum computer that can scale to solve the kinds of problems we're trying to solve is that we have to take a full stack approach and think of control at every different level of building that quantum computer. And you may have seen this sort of a diagram in other presentations, but I want to focus on something a little bit different this time, which is how do we design and tune those pulses that most directly interact with our quantum device? Because when you get right down to it, we need high fidelity control so that we can pay as small an error correction overhead as possible. And one way to do that is to start with a pulse that accurately controls the quantum device we're trying to work with. So we might draw something down like this, where we feed in some stepwise function for a pulse. But the trouble is that when we do that, we actually get something that looks much more like this. We might have ring down, we might have crosstalk, we might have other sorts of distortions. We'll definitely have noise, right? So we have a lot of other things we need to worry about that make it hard to actually design that control. Now, because this is a Bayesian talk, I'm going to start it with my prior, right? So what prior work is already out there? And it turns out there's a lot known in this area already, largely falling under the heading of optimal control theory, where we start with some Hamiltonian, we assign some parameters x to represent what we don't know, and we go learn it. We might do a Hamiltonian learning experiment like Robbie-Ramsey, try and characterize, or something even more complicated. And once we have that Hamiltonian, there are lots of good algorithms for turning our knowledge of that Hamiltonian into a control sequence, something like GRAPE, gradient descent pulse engineering, something like CRAB or DMorph. Maybe we'll even use something like etc. There's more names there. Etc. is not the name of an algorithm. But there's a number of things that go wrong with this that mean that optimal control theory, as wonderful as it is, doesn't get us everything we need. So for one thing, we're kind of prematurely optimizing the wrong model here, in that no matter how well we've learned the Hamiltonian of our system, there's still some finite uncertainty, and it's not going to be a complete description of the system we're trying to control. And the actual system that we're trying to control will behave somewhat differently, and we'll get a worse control because of it. And in particular, we need to know a full model of the experimental system. What noises, what distortions. And we can start including all of those in, but then we run into the third problem. That's actually very computationally difficult to optimize, especially as we grow the size of the system we're trying to control. So in light of this, one of the things that we've seen in literature in the past several years is that we can solve this by actually testing how well control works, going to the actual device that we're trying to control and using it to test its own control. Now, if that sounds a lot like randomized benchmarking, that's because it is, right? In randomized benchmarking, we do random sequences of controls to characterize how well that system is the fidelity of our control. So that is, in the same case here, we'll take some pulse that we're trying to learn about, and we'll do randomized benchmarking with that pulse. So that consists of doing random sequences of Cliffords, the noise following each. We can rewrite that circuit as a different sequence of Cliffords that conjugate the noise, and that gives us effectively a sequence of depolarizing noise that gives us a nice exponential decay that we can go learn about. And the rate of that exponential decay tells us about how well the control worked. Once we have that, we can optimize. So ad hoc and orbit, there are two algorithms that do this. They use Nelder-Mead on the control landscape to iteratively improve a pulse that you get from optimal control theory, maybe starting with around 99% fidelity, to something that looks a lot better, a lot closer to the kinds of qualities we need to get that error correction overhead down, something closer to 99.7%. ACRONYM improves on this by using stochastic optimization instead, because when we estimate our randomized benchmarking parameters, it's just that, it's an estimate. There's some noise left. And so using a stochastic optimization algorithm instead means we can start from a much worse starting point to get to that where we want. Both of these, though, encounter another challenge, and that is that randomized benchmarking still takes a lot of data, especially when I use it at the inner loop. So let's be Bayesians about this and update our methods. So, thinking about randomized benchmarking, the trouble here and why things are as expensive as they are at the inner loop is because we've thought of our randomized benchmarking parameters that we're optimizing over as being kind of an oracle. I go do an experiment, I get back a number. But that's not quite it. They're the result of an estimation procedure. And that procedure, here I'll describe it in a Bayesian way because it'll be convenient in a couple slides from now. But it's a procedure where I take in data and I improve my knowledge of some randomized benchmarking parameters iteratively. And I get back at the end, not just an estimate of those parameters, but a full posterior that tells me about my uncertainty and the probability that those randomized benchmarking parameters take on each value in this range. So for instance, here I can see from the width of that posterior what my uncertainty in that randomized benchmarking parameter is. Now, what's really neat about this is that prior information can make that go a lot faster. If I go in with a distribution that's already fairly tight and I'm just looking to narrow it, that's a lot easier of a task than if I have no idea what the RB parameters are and I'm trying to learn well enough to iterate. So the big idea behind ACRONYM, behind what we'll do to take ACRONYM into a Bayesian context, is we want to reuse the information at different evaluations of this RB oracle. We want to, when we explore a different control sequence, use what we've already learned at the control sequences we've already looked at. And this seems like it could work because our RB parameters are often very smooth in terms of the knobs that we have to control in our sequence. So here, for example, is a nice little over-rotation problem where, as we change our over-rotation angles, we actually have some idea about what the next fidelity could be given where we're currently sitting. We don't know if it'll go up or down, but we know about how far it could possibly move. So can we use that? Yes, we can use that. Our main result is that the average gate fidelity changes smoothly with the pulse that we apply under fairly weak conditions that I'll talk about in a moment. And in particular, that we can then use the posterior at one optimization step to make the prior for another optimization step, reusing knowledge throughout. The main technical tool that we'll use to formalize all this, make it rigorous, is Lipschitz Continuity. I've talked a number of times about things being smooth, but we'll formalize that by saying, if we can slide a cone along our function and the function stays within that cone, then we say it's Lipschitz. More formally, if the distance between the function at 2 points is no more than some constant times the distance between the 2 points I evaluated at, then we say that function is Lipschitz. This definition extends nicely to channels if I use the notion of distinguishability. So here I'll say that a channel is Lipschitz if for all density operators, it doesn't make that density operator very much more distinguishable. I can't distinguish the action of that channel on that density operator very much. So in particular, the trace norm between that channel at some control parameters and that channel on a different set of control parameters acting on the same density operator can't be larger than some constant times the distance between those control parameters. Once I have that, then the first step is to prove that my RB parameters are actually Lipschitz when I do interleaved randomized benchmarking. And for this, we'll need two lemmas. The first one is that the product of two channels that are each individually Lipschitz is also Lipschitz. And we know this has to be the case, otherwise we could violate Hellstrom's bounds on distinguishability of quantum states. And to see that, if I go back to the previous slide, I express smoothness in terms of distinguishability. If by applying a second set of controls, I could distinguish which set of controls I applied first. I could use that to break distinguishability bounds. So we know that product of two smooth channels is in of itself smooth. The next lemma we'll need is that if I have a convex combination of smooth channels, that it's also smooth. And here the proof follows by writing out a bunch of telescoping sums and applying triangle inequality. It works exactly as you'd hope. So if I take these two lemmas and I write them down on the left, I can use them to get to the two theorems on the right. In particular, if a channel is Lipschitz, then so is the fidelity of that channel. And in particular, if a channel is Lipschitz, then so are the RB parameters of an interleaved experiment that uses that as a reference. And here we have to worry about all of the sequences that involve that channel, not just single copies. So that's why there are distinct theorems here. At this point, I think it's helpful to kind of show a bit of an example. So let's say that we're doing randomized benchmarking using H's and S's to generate our Clifford group. And we'll suppose that our S has some over-rotation, such that if theta is 0, we actually get the right gate, but otherwise we have some over-under rotation by that theta. We'll put some noise on each that's depolarizing, just because it's simpler to work out here and see the example. But then we can use the previous theorems to show that the RB parameters in this case are a smooth function of theta. We can do so by writing out what the reference channel is. So that's the average noise that we get in each unitary in our twirling group. And so we're done if each of those, the noise in each of those unitaries is itself smooth, because then we can apply the convexity lemma and we've got it. So let's actually write out what each of those lambda u's is. And we can do that by writing out each of those u's in terms of what gates we needed to use to get them. So for instance, if I want to write out h, well, I'm done. I just use h. But if I want to write out other members of the Clifford group, I might need to use 1, 2, 3, or 4 copies of S in that expansion. We can apply the product lemma to each of those sequences. And since the noise in H, whatever it is, doesn't depend on our controls, we're only looking at S at the moment, we don't count how many H's. We only care about how many S's in this example. So identity and H both have no dependence on our control parameters. S, H, SH, and HSH all pick up 1 copy of S, and so forth. And so from the table above, from this table, we get that on average, we have 13/6 of a copy of S in each member of the Clifford group using this expansion. If we use a different expansion, we might get a different number, but that's what we get in this case. So applying the convexity lemma, this gives us that our reference channel is smooth with a constant most 13L/6, where L is how smooth lambda S itself is. And so as a corollary, when we do interleaved and pick up one additional copy of lambda S, we're at 19L/6. For this simple example, we can actually compute what L is directly, though, by substituting in our over-rotation error. More generally, this is where an assumption comes in. This is where we say something about the underlying control model. But in this case, we get from that L is 4. And when we apply the dimensional full factors for transforming between RB parameters and fidelities, we end up that at 76/3, that's a small enough number that we can actually say something about how P changes as we change our over-rotation angle. How do we use that? So we use that by expanding our posterior at each step. Now that we have this smoothness, we can say if we're trying to estimate a function that is smooth with respect to some parameter, and we change what that parameter is, the variance of our estimate, the variance in that function does not change very much. In fact, it changes roughly proportionally to that Lipschitz constant itself. So that is, we have a limit to how far each hypothesis about those randomized benchmarking parameters can move as we change our pulse, and it's given by that same L we just computed on the previous slide. The convex hull of our support grows at most with that constant as we move things around. So to summarize, if our channel changes smoothly with our control sequences, then our posterior over interleaved randomized benchmarking parameters at one control sequence makes a really good prior for the next step when we expand in this way. Now, I've done something kind of underhanded here, right? I've only proved things, I haven't actually tested them. Because, maybe my proof didn't actually really apply, I didn't assume something. So we go and do the numerics as well as the proof, using that same example, because it's a nice example to work with. We can see how it works. And what's really cool is each iteration of this, we're using very little randomized benchmarking data. This plot here is of all the data that this Bayesian acronym algorithm uses to get from one step in the optimization to the next. And if I just showed you that, it doesn't look very much like a randomized benchmarking plot. But the thing is, I already had the whole history of the optimization up until then. So those points are enough for me to actually agree with the true RB decay that we can go and simulate. And doing that, we can actually find that optimal theta. Here we've chosen it to be 0, but we didn't give the algorithm that knowledge. We can go and find that optimal theta in less than 20 iterations. And we can get to that maximum fidelity we can reach before we hit our depolarizing noise in about 7,000 sequences. So an impressively small amount of data. So to put this all together, where did we end up from this? We proved that if a channel is smooth and the control parameters, then the randomized benchmarking parameters are also smooth. And that lets us reuse prior information when we optimize that smooth function. Reusing allows us to optimize very efficiently. So that's Bayesian acronym tuning, and it works, uses very little amount of data. So I'd like to close out by talking a little bit about, about Microsoft. We're a very global team. A lot of different sites around the world. I myself am over on the Redmond site, and a lot of what I do is what I've just talked about here, but the other half that I'd like to talk about for just one slide is we work a lot with trying to make it easier to think in terms of quantum algorithms using the quantum development kit. So please check out, there's a lot of different resources to let you try things hands-on without even installing anything. So please give it a go and get involved. Thank you much for your time.
All right, thanks, Chris, for the talk. We have time for some questions. There's a question in the back.
Hi, thanks for the great talk. Could you comment on if you think your Bayesian approach would be more or less susceptible to systematic drift in the parameters?
As phrased, more, but that's a thing that you can include. I didn't talk about it here or in this paper because there's other papers that talk about this, but it's relatively straightforward to include drift in a Bayesian framework like that. So if you just run things the way I presented, yeah, you're right, that's going to be worse. But it's a framework you can start adding other pieces like drift onto. I'm not sure what that would imply for the final efficiency, but you could include it, and then, yeah, you'd get an accurate answer out that way.
Another question here.
In the pulse optimization, are you restricting which aspects of the pulse modifications that are taken into account here?
Yes, so in this case, it was a really fairly simple example just to kind of prove the point and make sure that mathematics actually match what we're trying to do. So there we really were just trying to adjust the over-rotation, under-rotation angle. But there's nothing in principle, like, what you really need in order for this to work is you need to match you need for your channel to have some finite Lipschitz continuity in terms of your control knobs. And the smaller that constant is, the more efficiently you can reuse information.
More questions? Yeah, there's one over here.
So since you mentioned crosstalk in the beginning, like would this technique work with errors like that?
I mean, the same thing, really. The only assumption this really makes is that whatever your fidelity is, whatever your channel is describing the effect of your control sequences, that it's smooth in terms of the knobs that you're trying to optimize over.
But so would you expect it to be smooth in that case?
So maybe it's helpful to say what it would look like if it's not smooth, is that there would be some control setting that as you move, you would have an infinitely you'd have an infinitely steep change in the response of your system. So I mean, even this is a very weak assumption, and that even something that oscillates pretty wildly with your control knobs will still have a finite Lipschitz continuity often. It just might be so large that you don't get to reuse as much as you'd like.
So like a square root function would be an example of a function that doesn't have a Lipschitz constant, right?
I mean, depending on the domain that you're changing the controls
around
over.
the origin.
Yeah, yeah.
Other questions?
So I guess my experience, and by my experience I mean the experience of the experimentalists, not me, whenever they get some pulse that's designed by something fancy like grape or whatever, and then they try it on the experiment, it never works. And this is always explained as, well, there were pieces of the Hamiltonian we don't know. So do you have, I mean, it seems like from this that you proved this is going to work, but do you think it'll really hold up under actual experiments? And are you going to try some?
Well, okay, so in a part, this is a response to exactly the point that you're raising, right? That, I mean, done a lot of research in learning Hamiltonians precisely so that you can go stick them into grape. And I've seen a lot of success from that, and I've also seen a lot of the failures you're mentioning. And so we're kind of trying to flip it on its head and say, let's actually use the system to test itself. And we know that this works. People have done it with Orbit, and they've done it with ad hoc. So what we're trying to look at here is, we know that works. Let's make it fast enough that we can do it in practice. So that's why we really didn't focus on whether or not it works. In general, we know that we're building off of prior work here and trying to make it more efficient and proving that we can do so rigorously. So I expect from our experience in the literature and from what we've shown here that yes, it should work in practice as well.
Okay, any other questions for Chris? All right, if not, let's thank Chris and all the speakers of the session.